In the previous class, we managed to work with the basics of the nozzles, if we remember. And I said for each and every part that we are going to have later on, these nozzles, they are going to be following the concept of convergent, divergent in terms of the shape. So in this case, we have a special part that we are going to look into on its own, which is the gas nozzle or the gas nozzle. From this one, its properties will be different somehow from what we had, from what we are going to have later on the steam. So when we are dealing with the gas, let us just go back to our gases, guys. The gas laws. Air can be used. When we work with the air, it means we are going to have an effect in terms of the adiabatic index. When we consider this part of our nozzles, this is what I want you to understand when you consider the part of what of the nozzles. The air, as we have, remember, the cross sections there are different. The cross sections are different. So as the air enters or as the gas enters at the inlet, take note, it is entering at the inlet. It enters at a certain pressure, which is our P1, up to when it comes to the exit. So the question is how? How does it in terms of this convergent divergent nozzle, how? Or in terms of the pressures, how are the pressures going to be given? How do we apply the pressure? So if we consider the issue of our pressure, we are going to notice that the pressures will be different from the inlet to the outlet. The pressures will be different. For a different pressure, that means we are going to have a difference in terms of the volumes, temperatures for the inlet and outlet. And also, because the pressures, they're different, the pressure here is different at the pressure at this point, it means even the temperatures at this point of the throat, the values there, they are not going to be the same as what we have here. They are not going to be the same as what we are going to have different values. So that's what I just want you to understand. Remember, we said a nozzle is a duct of smoothly ragging cross-section area where a steadily flowing fluid can be made to accelerate by a pressure drop along the duct. So the pressure will be dropping. There will be a pressure drop, and that causes these values not to be the same. So I just hope those things okay, they're not, they can be useful somehow. Let's go to the diagram, guys. We do not want to waste time and do the calculations that can help us. So remember, like I said, we are going to be dealing with a convergent divergent nozzle. So we're going to be dealing with a convergent divergent nozzle. All right, so let's just say this way. So, okay, this one is now like trying to be, okay, something like this. So let's say this is where we've got our throat, and there we have got our exit. Okay, this is 1, this is 2, this is C for the throat. So this time, we are not going to be having this enthalpy, this one. We are not having this one this time. This one is not going to be there. We're just going to have the rest at that point, all right? So we're just going to have the rest of those values, meaning to say they are going to remain as they are: the pressure, the temperature, the volume, the velocity, and the area. So the same here at the critical values at the throat. We're going to have the same thing: PC, TC, that's VC, CC, that's AC. At the exit, all right, so this is inlet. Remember, this is our throat, and this is our exit. So at the exit, the same thing. So we're going to have P2 in terms of pressure, P2, that's T2, V2, C2, and A2. So this is what we are going to be having actually for gas. The calculations can be made, and guys, the formulation of these, I'm not going to go into that. What I just want you to understand are the formulas. The reason being is that we have some of this part. If we consider our formula sheet, they gave us some of these formulas. So guys, I'm not going to waste much time from the pressure, this and that. You're just going to need adjustments on those formulas if it is necessary, but most of these formulas are there here. Yeah, like almost everything. Okay, so that's why I'm not gonna go into the formulation of these formulas. So what you're going to need on the calculations at the inlet, mostly you are given the values there. They will give you those ones. So unless you are to manipulate values to obtain what is of the inlet, unless you are to manipulate. So in most cases, our calculations will be on the critical values, which is at the throat. All right, so at the throat. So I want you to have these calculations, guys. At the throat, remember that's where we use the subscript, that's where we work with the C. So we're gonna work with the pressure. So PC is equal to, that's 2 over gamma. So we use gamma if we are working with gases. Remember, we were talking about the adiabatic expansion. Right, so that's, okay, I left P1 here, sorry. It's supposed to be P1. That's P1 into 2 over gamma plus what? Plus 1 to the exponent, as it is on your formula sheet. So there are a lot of formulas, guys. Just that you need to understand them. So like I said, that is when we are dealing with what? With gases, we work with what? We use the gamma there, the adiabatic. Then also we have got the temperature, TC, which is equal to T1 into 2 over gamma plus 1. Okay, that's our TC, which is the critical value at the throat. Then we also have at the throat, the volume at the throat can be calculated. For a kilogram, we take our mass to be 1 kilogram for that moment. So our formula will be given as RTC over PC. The reason it is because we are using the mass at that moment to be a kilogram. So therefore, this volume that you are calculating is going to be in cubic meters per what? Per kilogram. I think I mentioned that one in our previous class. All right. Okay, where was it? Or did I remove it? Oh, here on the volume. Cubic meters per what? Per kilogram. So those are the units that you're going to be having. It is affected by the issue of always you take that mass to be 1 kilogram for that. So that's per kilogram of what? The mass. We also have the velocity at the throat, which is the velocity is given from the formula. The formula was supposed to be the square root of 2 CP like this into T1 minus TC plus C1 squared. So this one, the specific heat capacity there is supposed to be in joules per kilogram. We are supposed to have it in joules per kilogram. So to obtain that, we must multiply by 10 to the exponent of 3. So you end up with 2 times 10 to the exponent of 3 to get rid of kilojoules. Remember, when you are given these values, it will be what? Kilojoules. But you're supposed to use it in joules per kilogram. So that's why you see on your formula sheet, it's written as 2000 like this. So it can be 2 times 10 to the exponent of 3. All right, into, so that's 2000 times what? The CP. So meaning to say, when you use it like this, your CP is joules, is going to be kilojoules, because already you have what? Used the times 10 to the exponent of 3. So when you use the 2000, you use the CP as it is. Remember, times 10 to the exponent of 3 was to get rid of that kilo so that it becomes joules. So that was of the conversion to get rid of what? Kilojoules. This one, the 1000, this one is to get rid of the kilojoules that are here. So meaning to say, CP as we have it, it remains as it is in kilojoules per what? Per kilogram as you are given it, because you have already removed that kilojoules by what? By the 1000, this one that we are seeing here. So there won't be any effect once you do this adjustment. So that's why you see your formulas in the formula sheet, they put that one so that you won't make mistake. You just use the CP as it is. All right. So that's into T1 minus, okay, we are at the throat, so that's minus TC. Okay, we are supposed to add plus C1 squared, but remember, guys, we said that one is very small, that it can be neglected. But guys, you know your textbook, some other textbook, this one can give this way, another textbook can give this way. So it was supposed to be plus what? C1 squared, but this one can be neglected since it's very small. The C1, very small, that it can be neglected. So you take it to be what? 0 meters per second when it is of that nature. So that's it. We have got this one. Like I said, guys, the units we talked about velocity in meters per second. So you have your velocity in meters per second. Another part is the area. So the area at the throat is going to be taken from the mass rate. So there you use the mass rate, kilograms per second, all right, times the volume that you had at the throat divided to the velocity at the throat. So take note, this one is in what? Cubic meters per kilogram. The velocity, meters per second. Meters per second. So this one must be in kilograms per second so that it gets rid of this one, so that our area can be in what? In square meters. Like I said, for calculation, your area will be in square meters, but conversions can be made. All right. So this one, our mass rate, supposed to be what? Kilograms per second. So you must convert to the kilograms per second. So these are the calculations that you will need. So this one is an interesting topic, guys, that you're going to see. It's an interesting topic because you have to work with formulas. A lot of formulas, manipulations. Okay, you'll see. You'll see, guys. Let's have the exit. Like I said, at the inlet, those are the ones that you'll be given. If you want something about the inlet, you just have to make it the subject of the formula from where it is, if it is not given. All right. So at the exit, let's see what we have there at the exit. So at the exit, we're going to use 2 for values which are at the exit. So there we are going to consider, we do not have a lot there, T2, which is equal to T1 into P2 over P1 to the exponent of gamma minus 1 over gamma. This is from our gas laws, all right? If you consider our gas laws, let's go back here where T2 is. Remember T2 over T1. T2 over T1, we just make T2 the subject of the formula here. Remember, we are dealing with this one. So we just make, okay, I need where there's pressure. Where there is pressure here, this one. So you just make T2 the subject, take T1 to the other side, you multiply it there. So that's it for the temperature at the exit from your gas laws. Like I said, please do revise your gas laws. V2, the volume, can be calculated from the same concept of this one. So that's RT2 over P2 this time per kilogram, because you used M as a kg, as 1 kg, 1 kg. So your answer definitely must be cubic meters per what? Per kilogram. Okay, so that's it on this one. C2, the speed or the velocity there, that'll be the same thing, just like this one I explained how to get rid of that kilojoules. So you're going to use 2000, all right? Cp into this one is going to be T1 minus T2. You are at this point, so it's T1 minus T2. All right, so that's T1 minus T2. You are supposed to add that C1, guys, like I said, but that one is equal to 0, that it can be neglected. So you can just write it, but there's no need for this one because it can be neglected. Okay, then we move on to another part, which is the area. So A2 at the exit can be calculated again, just like the previous case, mass, which is the mass rate, the volume at the exit over what? The velocity at the exit. So that will give us the area, just like what we mentioned here, the same things. So that is how we can have this part. And also they can ask you to calculate what you refer to as the mach, or I don't know, how do you call this one? Mach or Mach number. The Mach number, which is a ratio of the velocity at any point along the nozzle to the velocity of the drop. So meaning to say, as we calculate our Mach number, it's going to be velocity at any point over what? The velocity at the throat. So that is at any point, it can be 0.1, where 0.1, guys, we know that mostly it's 0, they're neglected. So meaning to say, you're going to work with what? C2 at the exit, where we have what? A value. There is a value that is what? Calculated. Remember, your velocity can be calculated in what? In meters per second. We have a value that can be calculated from there. Okay, so this is a basic of what you are going to need. Like I said, yes, I just need to mention everything, then we finish, we do examples. Because if we have these formulas listed, we consider other formulas again, is gonna affect. So let us just finish up with the nozzle efficiency. So we can also consider this part of the calculation of the nozzle efficiency. Okay, so to understand the issue of the calculations of the nozzle efficiency, it is best that we do understand it in a way that when we deal with a gas, remember, we can consider what we refer to as an ideal gas. All right. Remember, we have what we refer to as an ideal, which is a condition where you are working with, this is the condition of the adiabatic expansion. All right. This is the condition of what? The adiabatic expansion, where in this case, efficiency will be actually 100%. Efficiency will be 100%. Meaning to say there is no effect. There is no effect in terms of the friction. It's a frictionless path that has been taken for that part, for that consideration of an ideal. But we are not going to have that one in a practice, guys. We are going to definitely have friction considered. So at the end, there are effects in terms of the temperature, in terms of that in terms of the that change in terms of the temperature affects our efficiency at the end of the day. If we are dealing with the steam, we're going to talk of something else in terms of the steam. We'll be referring what is going to affect the efficiency. But as we have the gas, remember, we are under a gas nozzle. The effect of that friction will affect, at the end of the day, our temperatures. So I want us to consider, on a basic view, when everything is perfect, from our TS diagram, temperature, entropy diagram, we are going to notice something like this when everything is perfect. No friction, nothing. Temperature, and this is our entropy. This will be P1, okay? So in terms of the pressures they'll be affecting. So we are going to notice that. In this case, we have one point to another in a straight line. There is no effect there. From point 1, as we have our pressure, this is P1, this is P2, this is of what? The throat. So at point 1 here, this is where you are starting. The temperature is corresponding to T1. At C, we are going to notice that here it will be straight to the throat. So there is going to correspond, this is of the throat. The temperature for the throat, it goes straight to the exit, where it corresponds to the temperature of the exit. So this is TC, this is T1, like that. In this case that we are having here, from stage 1, in this path 1, to, C to 2, like this. Guys, there is no effect there. That's an ideal. So when it is ideal like that, there is no effect in terms of efficiency. Your efficiency will be 100%. But this efficiency, due to friction, we are going to see the diagram affected due to friction. So due to friction, let's see what's going to happen now. So due to friction, the first part that can be affected is the diverging part only. So let's say friction on the diverging part. When we have got friction that is affecting the diverging part only. So the diverging part will be seeing the effect from the critical here. Remember, when we had our first class, guys, let's go back to our first class when we had that convergent, divergent. The part of the diverging, it will be like this, from the throat to the what? To the exit. So we are starting from the throat to the exit. So we're just going to consider C to 2. So this is the condition from C to 2. So we are moving, the effect happened from C to 2. That's where the effect happened. the part of the diverging from the throat to the exit. That's where the effect happened. The effect, guys, remember a convergent, divergent. Convergent is like this. When it is converging, we start like this, guys. Remember your convergent from this one to the throat, from inlet to the throat. Then from the throat to this one is now divergent part. So we are starting from the throat to the exit. So we are going to notice the effect from there, the diverging part from C to what? All right, from C, which is at the throat, to the exit. So meaning to say our diagram is going to be affected. We are going to see our TS diagram this way. Okay, that's our temperature, entropy, like this. So this is what's going to happen, guys, as we had previously. Okay, so here from P1, this is our throat, this is our P2. From 1 to 2, I mean from 1 to the throat here, from 1 to the throat. Remember, from the inlet to the throat, it is actually the convergent part. So we are not worried about the convergent. It is not affected. That is from 1 to the throat. We are worried from the throat here to the exit where we are having the diverging part. So meaning to say, it was actually supposed to do like this. Remember these values, it was supposed to be these original values. They are supposed to be 1, C, 2 like this. So it will move with original value from 1. I mean, the actual value is going to be at 1. At the throat, you are going to be having the actual value for C. But 2 is not going to happen like that here. It is affected because of the friction. So the diverging part here is going to be having our 2 at another value, not where it was supposed to be here. 2 is not going to be where it is. 2 is affected. So we are going to notice our 2 having this condition like this. So that is what is going to happen here. So this will be our point 2. So what about this one? Because we are supposed to still have our adiabatic expansion of that ideally. It is supposed to still occur. That ideally is supposed to occur. So that is going to be the reflection of these 2 will be what? Will be 2 bar. Those are the adiabatic ideal values. So this is the condition. So this will be our adiabatic part, this one, like this. That will be our path. And this path 1C2 like this is of the what? Exact or actual values. Where there are those absolute values, it means there is efficiency there. We are talking about practical things. So definitely it's not ideal. It's not ideal. So there will be what? There will be efficiency there. So this is what I'm trying to say, guys. So as we notice here, another thing is we analyze what is happening on our TS diagram. Remember this point C1, okay? So this will be like T1. Here it will be what? TC. And here it's going to be what? T2. And in terms of the temperature here at this point, we're going to have T2 bar, which means there are now 2 temperatures at 2. At this 2, there are now 2 temperatures, an absolute, an actual value, a polytropic value, this one, and an adiabatic, an ideal value. So we can calculate this. So it follows that T2 bar, which is our adiabatic, from adiabatic expansion, because it's an adiabatic value. So it's going to be the one that we take from the adiabatic expansion. So remember, we are moving from where? From C to 2, the exit. So meaning to say it's just like you are calculating T2. Then you say T2 is equal to T1 into P2 over P1 to the exponent of gamma minus 1 over this. So it's from where you are from T1. Here we are from TC. So this one must be TC, this one must be PC. That's it. Guys, yeah, you know, the Nozzles part is that they need you to understand everything about your power machines. And once you do that, guys, you are done. You are done, guys. You are done. There's nothing here. There's nothing. There is nothing at all. Just revise your basics of N5. So that's it. We have got what? Adiabatic temperature. Okay. Ideal. Then T2, this one, which is the absolute value, in this case, can be calculated because it's still from where? From TC. Remember, TC is not affected. There's no TC bar, so it's going to be taken from the same TC. The pressures, they are not affected. So it's P2 over what? Over PC again to the exponent of what? Because it is an actual value that you are dealing with. If you are dealing with an actual value, you are dealing with what you refer to as the polytropic expansion. The absolute value is from the polytropic expansion, this one. All right, so that one is in a polytropic expansion, meaning to say we are going to use N. So that will be N. Remember your guesses, guys. Adiabatic, you use what? You use gamma. You use gamma. So that's it. That's it. Just like that. So meaning to say, here we talk about the temperatures. We are not into the efficiency. Remember, the major part here, guys, is about what? Efficiency. So let me write the formula here for the efficiency. I'm going to write them, all of them at once. So in this region or in this section of the diverging part, where the friction affected the diverging part only, efficiency can be determined there. So this is the one. Also, you're given it from your formula sheet. I'm going to explain this one from the formula sheet, how it is given. Then I'm going to write the one that I'm going to write here, but I want you also, because some are using the formula sheet for revisions. Okay, there are people who are like that. There are people who are like that. We are not the same. They are not the same. So for those ones who are using the formula sheet, I'm just going to talk to you now. Okay, so this is where you're going to have, remember we are dealing, this is the new formula sheet, guys, for the new syllabus. Okay, don't use the old one. This is where we have the diverging, for the diverging part. You remember we're dealing with what? Gas nozzle, we work with temperatures. So this will be the formula, temperature at the throat minus at the exit at the throat minus. So this one, the one they're writing as T2S, is that part of what? Our adiabatic value from that adiabatic expansion. This is our T2 bar according to the way that I was explaining there. So this one you write as what? T2 bar. That ideal value. So I hope we are together on that one. So let me just have the formula. So that is it. We can have our formula that way. So the efficiency, which is our diverging efficiency, can be determined from there. So that will be TC minus T2, TC minus T2 over what? TC minus this one, T2 bar. So that's it. That's the diverging part. Here we are working with this part only. So if you understand from here, guys, I think it can be clear. So if we go back to this one that we had here originally here on this one, where we said is the converging. So converging, what happened actually? When it is converging, it means the opposite in terms of the direction now. We are working from, okay, remember converging, here it was fine, it was diverging. And so converging, it will be like this. Remember the diagram of a convergent. It will be like this. Convergent, it's from a bigger one, like this. So it's going to be from 1 going to the what? To C, to the throat. So it is 1 to the throat. So if you understand that way, guys, here it was from the throat to 2. So if you understand that it is from 1 to the throat from this one, it means the throat is the one that is affected. In terms of its temperature, there will be the exact value and there will be an absolute value there. So meaning to say that efficiency will be just affected in terms of the temperature there. So meaning to say when it is a condition of a converging, it will be T1 minus TC, okay, just like here, then it will be T1 minus TC, like that. Okay, so for which here, guys, I want you to focus on this part, the diverging there. So that is it. We have got our efficiency. We have got efficiency. All right. The last part, like I said, I'm going to try to combine them. I'm going to try to combine them, all of them. I just hope this board is not going to affect it. So you see, if I do a class of 30 minutes or this board start to just drag, I don't know. Guys, what these softwares need us to do. They want us to work with what exactly? I don't know. Anyways, let us move on. Remember, we dealt with the friction in the diverging part only. What about if we consider the whole section of the nozzle? The whole section of the nozzle, we are back to the convergent, divergent. All right, we are back to where it is from the shape that we are working. So what if the friction affects the whole of the section? Friction due to converging, diverging. What is going to happen? So the whole part here is affected. If I bring it, let me bring it this side, guys, so that you understand me. If I put it here, remember here we affected the diverging. So now we want to affect the whole part from this original. Let me use this original so that we can understand each other. So the whole of the section now, that will be our overall efficiency, the nozzle efficiency. You are going to notice that if it is overall where the friction is affected, we are starting exactly from point 1 up to the end. Remember the first one, it is 1 to the throat, which is the converging, where this one is going to change. This is C and this will be C bar. So meaning to say we're going to consider TC and what and TC bar. So that is the one that we ended up with the converging efficiency. Now we are saying now and another one after that, we said the other one will be from diverging, where you take from C to the what? To the exit, where this one is affected. This is 2 and this is now 2 bar. What happens now if we take it from the inlet where it started, because it's now overall, so it will be like this. The path is going to change. So it means the path is no longer following 1C2 like this. It's following it this way. 1, this will be our C, and this will be our 2. So these become the corresponding values of the adiabatic, that ideal. So meaning say here we're going to have C bar, and here we're going to have 2 bar like this. So in terms of the This is what is happening in terms of our diagram. It is taken from 1 now, from 1. So this will be it, guys. The temperature is T2. This one, guys, I saw. Just like what we had before. So meaning to say the overall nozzle efficiency in this case, since it is taken from T1, so it will be T1 minus where it is ending. It is no longer ending at the throat, like what we saw before, where it was T1 minus TC for the converging. It ends at 2. So it will be T1 minus T2 over what? T1 minus the T2 now as a diabatic value. That's it. We're done. We are done. We're done with this one. So you need to just understand the basics, because not all conditions are going to be direct. But for this one, if we're dealing with gases, it's not that much. For heat, that's where you need to understand this diagram, because for heat, you'll be talking or you'll be referring to another type of a diagram. You'll be working with an HS diagram. That one is important because remember, there are steam tables and also the HS diagram, which is going to help you to find some of the values. But as for this one, guys, that is what you're going to need as of the efficiencies. So meaning to say, with this being said, let's go back here and just have everything concluded. So as we had our formulas here, let us just list those ones for the what? For the efficiency. So okay, another thing. All right, I talked about how to calculate T2 bar, isn't it? Yes, I talked about this, and how to calculate. All right, those ones I talked about them. Okay, sorry, let me just finish here. Maybe someone might want to know what about the path, but I think here, guys, is direct. The path 1 C1 C bar, this one is what? This path from 1 to this one to this one. That is our adiabatic, like I explained before. So there we work with what? With gamma from 1 C bar to 2 bar, I explained. So you're going to work with what? With the gamma there. Those are adiabatic. Then 1 to C to 2, those are exact values. Those are absolute, actual values. So whenever I work with actual values, those are polytropic, from polytropic expansion. So you work with N. So guys, it's direct there. All right. So these are the two paths that we can consider. All right. Let's have our efficiencies here. So efficiencies, we're almost done. Even my board is dragging right now. Let me finish. So efficiencies, number 1, we're gonna consider the converging efficiency. So converging efficiency, we said T1 minus TC over T1 minus TC bar. So that's converging this one. Okay, so that's converging efficiency. All right, I'm not going to write in full, guys. I'm not going to write in full for the sake of time. So this is converging. Some they can just use the efficiency like this with a C. All right. Then the diverging, they can just use a D like this. I'm just going to write dive like this, diverging. Okay. So we saw diverging from what? From C to 2. So the formulas, they are there. That's why I wonder why am I explaining this part, guys? But for the sake of revision, yeah, it's important. But they are there in the formula sheet. For those who do not understand the formulas in the formula sheet, I think I have tried to explain what you needed. Then the nozzle one, the last one. So this, yes, sorry, diverging efficiency. All right. Then the last one is the nozzle. So I'm just going to write nose, like this. So that's T1. Remember, this one is the overall from 1 up to the exit. So T1 minus T2 over T1 minus T2 bar, like that. The the nozzle efficiency has been calculated at the end of the day, the overall. So that's like an overall value. That's like an overall value. So remember, we talk about the pressure drop, this and that, as it is moving, there's a pressure drop. What is going to happen when that is considered? If they give us a certain drop from the overall, it means they are giving you nozzle efficiency. So the nozzle efficiency can be calculated as 100% minus a percentage drop that they give you there. All right? From 100%, because the nozzle efficiency is what? Is the overall. So they'll give you a percentage drop out of what? Out of from the overall. Percentage drop of what? Of overall, this and that you're given there. As long you are dealing with that drop, you can subtract it from 100% so that you have what? You have your nozzle efficiency at the end of the day. So this is it. These are the formulas that we are going to use. So like I said, this part of nozzles, it's an interesting topic. That's why I had to do this, so that when we are to do questions, guys, you understand me. It's an interesting topic. It's about manipulation. It means those people who are into mathematics, manipulation, something. And just like, guys, we know our engineering, play around with formulas. You write the formula, you find what is missing, you find another formula, you find what is missing, you find another formula, you find what is missing. Just like that. Fault finding. They are teaching you fault finding, guys. They're teaching you fault finding. So just like that part of your fault finding. This one is not working. Okay, let me pick this one. Just like that. But in your doing, know at least one or two things that this one cannot give me this. This one can help me. It is because you have done a lot of questions. So let us meet in the next class so that we dwell into more of this part as we do more questions.